good morning there, chemistry. It is day 71, where we take a look at the difference between this thing called KEQ, which we looked at last class, and Q, and get some idea how that works with exo and endothermic reactions. So being able to explain those and use those to predict the future is one of the main goals of today. A good thing that we can look at is this thing called the I-90 bridge. And if you look at the I-90 bridge, you'll notice it connects Bellevue and Seattle. And the traffic patterns, you'll notice that in the early morning demonstrate, of course, equilibrium at different points. In the morning, you'll see that there's tons of traffic that's heading west, making its way to Seattle for all those jobs there. Then by the end of the day, you'll see that there's a lot more cars that are traveling east, going to Bellevue to all those nice fancy houses and shops. And then if you go at the middle part of the day, you'll find out there's just that are going to Seattle to say get some of those nice restaurants, or back to Bellevue to come home to eat. Hey, it's reached equilibrium. And if we looked at a graph, of course, we'd notice at that point of the day, the concentration of Seattle would be a much higher population, and there'd be less of people in Bellevue, but they'd be making and breaking each other at the same rate. It's almost like, urban planners have to think about equilibrium systems. Now imagine what will happen if a light rail shows up and can easily send people back and forth. More people might decide to live in Seattle or in Bellevue and commute back and forth, and that's why, it was a big hubbub about creating that, because it's going to shift the equilibrium. Hey, it's almost like it's involved in real life. Nah, it's not in real life. Now, chemically, we should be able to look at these ones. We can see we got a little reaction to make some water. We got a reaction to make this CN minus stuff. Ooh, that sounds deadly. Doom, 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 doom. Write down the questions. Let's see if you can actually figure out how to solve a KEQ and then what it actually tells you. So this would be a good time to write down the questions. Pause me. Try them on your own. See if you got this stuff down. And here we go. If we look at this together, we can see, of course, it wants us to find what? It wants us to find the KEQ and tell us what it tells about the reaction. So the good news is we got a reaction. We can set it on teeter-totter. Hey, it's balanced. And we need a KEQ, so we're going to write an equilibrium expression. That's what a KEQ is, right? So that's the products over the reactants, and we can see this one, they're all gases, so I can use all of them because their concentrations can change. That's going to be H2O on top, the product, and that's going to be squared to the second power, right? Below that, I'm going to have hydrogen gas squared and oxygen gas to the 1 power. Cool. Now that I have those things, I can just plug in the numbers and roll, right? No. And a lot of people jump the gun and they start plugging in things, but remember that these little brackets, they mean concentrations. That's moles per liter. And these are just moles. So I got to do some math first. But the good news is that's easy to get. I'm trying to find my KEQ. That's my unknown. That means I need the concentration of water, of hydrogen gas, and of oxygen. So when I jug and plug these in, I'll notice the water was 1.50 piles of water, but that is in a 2-liter flask. So I have to change that to moles per liter, which comes out to 0.750 molarity, right? 75 cents, kind of makes sense. If we look at the next one, of course, for the hydrogen, you can see it's 2.50 moles of hydrogen, and that's going to be in every of those 2 liters. So it's like 250 divided by 2, so it's $1.25, and that's molarity now of hydrogen. That's a number that I can use. If I look at my oxygen, it was 3.00 moles of oxygen divided by 2. You're looking at yourself $1.50, right? 1.50 moles per liter of oxygen. Now, those are numbers I can use to solve my KEQ and plug them in. Plug it in, plug it in. So my water, I pull off the top there, it's 0.75. And that, of course, is for the water, and I square it. The hydrogen is going to be 1.25, and I square that, and that's 1.50, and I just put that to the 1 power. Now, what I would do, and I would suggest you do with your calculator, is solve the top and the bottom separately, and then actually take them and divide so your calculator doesn't turn against you. This would be 0.5625, and the bottom would be 2.34375. If you divide that out, you get a KEQ of 0.240, because the good old Siggy Figgy rules are pretty much the same all the time, right? And what's the unit? There is no unit, because it's a ratio. It's a ratio of the products to the reactants. So I've solved the KEQ. Now the harder question is, of course, what that means. Well, the one thing I should notice is the KEQ is less than 1. It's a Whittle number, right? So that means an important thing. That means that when I'm looking at this thing, when it's at KEQ, if it's a Whittle number, that means it's a Whittle pile of products. and there's a much bigger pile of reactants, right? It's larger in size. So that means that this thing reaches equilibrium. That's why it's KEQ. And at equilibrium, this reaction, of course, would be a reaction that favors which? Well, it favors more reactants. That's why there's a big pile of it. So this thing doesn't like to make products as much, and that's crucial. Now, what does that also tell me about energy? Well, I should be thinking about energy diagrams. If I was looking at this reaction, it likes to make reactants because that's the easier thing to do, which means that it's harder to make products, which means that the forward reaction is an uphill battle. Forward would be endothermic. Reverse is easier because there's a big pile of reactants. It's easier to go downhill, which means the reverse reaction is the exothermic. And this favors the exothermic like the universe always does. It's easier to burn a house down than it is to build it. So that's why this is making it a product, right? Now, what does this have to do with real life? Well, this is the exact reaction that's involved in these things called fuel cells. So if we look at fuel cells, of course, they're making water and using electrons traveling to do that. The only problem with this is as they're doing that, that can sap the amount of energy. So figuring out how to reduce this activation energy and get it to do it more easily would be a great way to find out, how to make a better battery and change the world. Oh, cool. Now, the other one, of course, is less about changing the world and more like secret agents trying to save the world. That's because this thing is hydrocyanic acid, also known as cyanide. And this is the cyanide ion, right? So this is what spies would, of course, take. And it can kill you in a couple seconds as it jams up your mitochondria. So this, of course, is not trying to solve that problem. It's trying to figure out what the equilibrium concentration of the cyanide ions would be. Well, that's handy. How do I do that? Well, I got a bunch of concentrations. I could use them in a KEQ, and they're giving you the KEQ, right? So first thing I do is I write myself an equilibrium expression. Products go on top. I got hydrogen ions because they're aqueous, and I got cyanide ions, which are also aqueous, and solutions can go in that. On the bottom, I got my reactant, which is this one thing called hydrocyanic acid, cyanide. And the cool thing is they're all to the power of 1, so it's not bad math. It told me the KEQ. It told me the KEQ was 0.34. Right? Okay, that's cool. And of course, the hydrogen ion concentration, they're telling you it's 0.40. The one you don't know, your unknown, is the cyanide ions themselves. So that's my X, my unknown. And then I got 0.50 on the bottom. So a thing that I should notice here, of course, is I can rearrange this thing and solve for my cyanide ions. When I do that, I would end up with a 0.34 because I'm just cross-multiplying and solving for X. It's like it's over 1, right? That would be times the 0.50, and then I put that divided by the 0.40 on the other side, and I end up with a cyanide concentration of 0.43 when you get SIGI with it for 2 units. That one does get an actual molarity because it's a substance and there's no brackets here. So if we look at the concentration of cyanide ions, it's 0.43. Now I can always ask myself, does this number make sense? Because I should always ask myself. Well, take a look at the KEQ. The KEQ, is that a big number or a little number? It's little. It's less than 1. So if I have a little KEQ, then that means that I'm going to have a bigger or smaller top, the products. Hey, I'm going to have little piles of products, right? They're going to be smaller, and there's going to be more reactants at the end of this because it's less than 1, right? So if I look at this, that means the cyanide is 0.43 and 0.40. Hey, those are less than 0.5. So this tells us an important thing. This KEQ was less than 1, so this reaction favors more reactants, more of the, hydrocyanic acid, cyanide. That means that, of course, there should be less products, right? Like the cyanide ions. And there is less products because that's a smaller number than the other one, right? What that means for your body, of course, is that there's less cyanide to actually clog up your mitochondria and you're less likely to die. However, it only takes a tiny little bit to do it. So even though this reaction, of course, is an uphill battle and doesn't like to make products, it's just a little bit of products that's required. Watch out, James Bond. Cool. Now, normally you would have done the tree sheet with the KEQ worksheet, but you got that other type of review with COVID time. The boys have been jamming. Boy, they've grown a lot since then. Now we need to take your notes out so we can talk about what we use this KEQ thing with. And that is to predict the future, right? So, we've talked about the Seattle Bridge. And one thing we can notice, of course, is at certain times of the day, there's more or less traffic, but at a certain magical time, usually around noon when people are going for lunch, The number of cars going back and forth stays, equal in terms of making and breaking Seattle, growing and destroying the populations of both. It's reached equilibrium. But if I went out here with a camera and I took a picture at any point in the day, it's a horrible camera, one of the things I would notice is I could take pictures in the morning when it's not at equilibrium. I could take them in the evening when it's not at equilibrium because there's a lot of traffic coming away from the jobs. Or I could just hit perfect and take a picture at 12 noon when they perfectly reached equilibrium. That picture, of course, could allow us to predict whether or not it's reached equilibrium. And the picture in science is called this thing called Q. So reactions are not always at equilibrium, but eventually they reach it. And how we know that is we take this thing called the reaction quotient, which is like a picture, right? And I like photography. So here's what Q is, right? Q is a snapshot at a specific time in the reaction. It can be any time. Here's what it's used for. It's used to predict if there's more product or reactant will be made to reach equilibrium. That's the crucial part. It allows us to predict the future. Now, the best news is this. You calculate Q the exact same way that you calculate KEQ, but then you compare Q to a given KEQ. And the Germans figured all that out. Now, the great thing is it's still the ratio of the products and reactants at any point in the experiment. It could be at equilibrium. If it's at equilibrium, that means that Q equals KEQ. Makes sense. It's the same ratio, right? However, if Q is less than KEQ, then the reaction will go to the right to make more products. It hasn't made enough products, so it's going to favor the forward reaction until it reaches equilibrium. Likewise, if Q is greater than KEQ, then it will favor the left, so make more reactants. It's got too many products, so it's going to favor the reverse until it matches up with KEQ. Pause it, write down the notes, and then we'll hit the other part. I prefer to draw this. It makes a lot more sense, right? So our brains are visual things. Let's use them. Let's say that we have a KEQ, which is my ratio of products to my reactants. And let's say that it's like 1 to make it easy, right? And I come along and I take a picture. We'll call it a Q. When I take my picture, I find out that the pile of products and the pile of reactants are exactly the same ratio that a KEQ is. That means the reaction's at equilibrium. Hey, I've reached equilibrium. Won't always happen, but it's going to happen eventually, right? Now, in addition to that, one thing I can see with this is, let's say that I take a different picture. And I find out that with my KEQ versus my Q, that my Q is bigger. It's greater than. Well, that means a simple thing. That means that there are more products than there are reactants. So remember that reactions are collisions. Who's going to run into each other more often? The products. And they're going to smack each other. And that means they're going to turn into reactants. So I made too much products. They're going to collide and make reactants until it matches the KEQ because it's too big, right? Or I could have the other extreme. I could have a Q and I take the picture and I find out that my Q is, well, actually less than the KEQ. Well, that's a pretty good indication if you think about the top. That means that the P, the products, is smaller and there's a big pile of reactants. So who's going to run into each other more often? The reactants. They hit each other and they're going to get converted into products until, of course, it reaches equilibrium where they're making and breaking each other at the same rate. They balanced out, right? So this, of course, is a pretty handy tool. If you think about the products on top, it's a big number, a little number that basically decides it for which direction it's going to go. This thing is going to favor, of course, the forward reaction. This is going to favor the reverse reaction. And this favors both reactions equally. Awesome. Now, let's see how we can use that. If we look at Q versus KEQ, that's the most useful type of problem that we've got going on here. And we've got this reaction right there. You can see I got some iron oxide, some ferric oxide, also known as rusty earth, iron ore, right? I'm mixing it with hydrogen gas to produce pure iron and water, right? And it's telling you something. It's giving you the KEQ, and it tells you it's 0.25 at 340 degrees. Wow, that's hot. It's almost like we're in a steel production factory, right? Not that our nation's built upon this reaction, but it kind of is, right? So saying, given the concentrations of those, find Q and determine the direction the reaction will proceed. Hey, you're predicting the future. So how do I do this? First, you write down the question. Pause me if you have to. Then we figure out our Q. Well, the good news is Q works just like KEQ. And it only works for, gases and aqueous solutions, things that can change. So my products, it's only going to be H2O to the third power because I can't have solids, right? It's the only gas. And my reactants, well, the only one that works is the hydrogen gas, and that's to the third power. Notice that the solids don't go in because they can't change concentrations. Then I can see that these are molarities, so they're numbers I can just use. So I plug them in. My water on top, my products is 0.060, and I'm cubing that bad boy. And then I've got a hydrogen gas, that's 0.46, and I'm cubing that bad boy. Pen's going to freak out. I'm going to solve them separately because I'm nerdy and always do that, so my calculator doesn't turn against me. There's the top. Silly pen. 0.097336 is the bottom, and then you divide and you get a Q, and your Q comes out to be 2 siggy figgies at 0.0022. Cool. That's the first thing they ask you to do. Then they ask you the harder part, to explain what it means. Well, I got to compare that to my KEQ. And what was the KEQ? It was 0.25 at 340 degrees. Notice it's for a specific temperature. So which one's bigger? Hey, Q is less than KEQ. So what does that mean, right? If my Q is less than my KEQ, I can think about it simply. I can say, okay, if we look at this, that means that when I look at my Q versus my KEQ, well, we can see it was 0.25, so there's going to be less products than there are reactants when it's at equilibrium, right? Making and breaking at the same rate. But I just figured out that my KEQ is actually less than that. That means that there's an even smaller pile of products compared to the reactants. So clearly, I don't have the right ratio. I've got more reactants, so it's going to favor making more products. It's going to favor the forward reaction. So if Q is less than KEQ, this reaction will favor the forward reaction to make more products. And then the key part, because Q has more reactants, so the reactants will collide more often to produce products. Hey, look at that. I've explained what its Q is and what its Q actually means. This thing hasn't made enough products, so it's going to favor that because it's got too many reactants, right? And you'll also notice a crucial thing. When I look at this problem, I can see that I've got an issue here. I've got, a claim, what it's going to do. I backed it up with reasoning, and I have my evidence in two forms, visual and written. It's almost like a great way to ask a test question, right? Now, what does this have to do with real life? Well, just think about energy. This is how we make steel, right? We purify iron from rusty iron ore, right? Hence the Pittsburgh Steelers, right? The Iron Barons and all that stuff. Now, key thing I can notice about this is this thing, even at equilibrium, doesn't like to make a whole lot of product. That's because it's an uphill battle. It has a large KEQ. It's not going to make a lot of steel for you, so you got to put a lot of energy into it. Hence the blast furnace to turn it up a notch, right? To jam it uphill. And that's why it even gets hotter than that, but I get ahead of myself in this part. Now, key thing that we normally do at this point is you would play around with this awesome thing called FET reversible reactions. You can see right there is my awesome link to go into it. It's another Java one. You can see there's hints about Internet Explorer being better at using that. Always think about this baby, right? It's an ugly baby. It's not my baby. My baby's cute. But don't forget to put up your dukes and think about all the variables of the gas law unit because they're coming in a roll here. What I want you to make sure that you do is you should make sure that when you play around with it, we normally have a worksheet to go with that, is you can change a couple of things. One, you can add in different particles, right? And you can let them run. You can let them do their thing. When they go and do their thing, of course, they can turn from reactants to products. But you can change a couple of things like this ruler, figure out what that represents. You can even change the stages. Whoa, look what the particles just started doing. That's weird. And you can change them on both the reactants and the products, which should make you think of an energy diagram. You can add heat energy to this. You can watch the temperature. You can even see these giant arrows up at the top. This are to do different things. They'll change if you change different variables, right? So play around with it and make sure that when you're doing this, man, they're not moving much. They're moving a lot. You think about potential and kinetic energy and what the different parts of this represent, because this is a powerful simulation if you actually think about it. But I'll let you do that on your own. Now, key things, normally we'd be going after the KQ versus Q worksheet. You're going to have some of those questions on your weekly assignment. And the FET reversible reactions, play around with that one. It's awesome. Make sure you think about KE and PE in your answers. Our target was to be able to explain what KEQ and Q represent. KEQ is the ratio at equilibrium. Q is a snapshot of the products versus the reactants at any point. If you compare your KEQ to your Q and they're equal, hey, it's at equilibrium. If you got a bigger pile of reactants than you do products, that's a pretty good sign. It's probably going to make more in favor of the forward. It allows us to predict the future. Very, very handy tool. Catch you later, Chem Geeks.